Right. Before we start Hooke's law, I just want to explain something called directly proportional and inversely, right? Do I have that? Do I have direct here? Anyway, it's here in the note, but I want to explain, right? So just take a look at this for one little second, please. Right. So sometimes, sorry, there one time. What has spotlight? Right. So I want to explain something called directly proportional, directly and inversely, right? So let's take a look at the concept of directly first, and then we take a look at the concept of inversely. All right. So let's say I said A is directly proportional to P. What that means is simply this. If I were to increase A, right, then the B value will also increase, right? So they both behave in the same way. If I were to decrease A, then the B value also becomes smaller. That's okay, right? So whenever you see the word directly, it's written like this, and this is what it means. If one increase, the next will increase. If one drops, the next will drop. That's okay? And there's a way for us to write that as a formula. This is not a formula. This is not an equation, right? Remember, equation must have a equal sign. So this proportional here is always equivalent to equal sign and some constant k. Okay? So I could rewrite this and write it like this. A is equal to k, because I'm removing this and I write in the equal and the k by. That's okay? And if I ask you to find k, which is a constant, k is equal to A over B, right? This is a constant, right? That'll all be the same. Okay with that? Right? So when you see the term directly, make sure you can write it like this and make sure you can get the equation like this. All right? If on the other hand, it says that the relationship is inversely related, right? The way I write it is like this. A is proportional to 1 on B, right? What this means is that if A increasing, B is smaller, right? If you play more game, the grade's going down, right? If you're spending less time on TikTok, what will happen? The grades will go up, right? So that's an example of something that's inversely related. And how you'll write it, A is equal to, take off this and put equal on K by 1 on B. You okay with that? Again, we could write it like this. K by 1 is K on B. If I want to find the K is equal to two fractions, equal sign, cross multiply. K by 1 is K, A by B is AB. That's okay? Yeah. So it's important when you see this word, you know what it means. When you see this word, you know what it means, right? If you never saw it before, you can write it down. Right? All the things you have though. That's it. Right. So we're gonna look at two quantities today that are proportional to each other. All right, so and remember, most of the times you need to find that K value, right? So all you need is an A and a B value to find K. Okay, there's also a graphical way, and I'll show you that just. All right, so today we're going to focus on hooks. That's our paper. Yeah. 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 Right, put form four out this week, next week, and the week after, right? After that, that's kind of time learning group. That's what I follow. Those who have exams and they want to come on next stage, that's what I'll tell you. If you want to come and practice, come up with testing, right? And you know, want to go on for lecture, right? Any day, every day exercise. I can even come to Saturdays as well. Right, those who write in Jan, right? Then the crash also in December, right? And I might do that one in Jan again, but I didn't want to do December, right? And those who have labs, remember to bring them for right up tomorrow. All right, so let's take a look at Hooke's law, right? Hooke's law is a law that applies to materials that are elastic. All right, so here we have a spring, right? This one's slightly damaged by your work for now, right? We have a spring, and what Hooke's law looks at, Hooke's law looks at how the force applied on this to this spring is how it related to the extension, right? And I'll explain what is extension just now, right? Let's say I give you a spring and we have a mass holder attached to it. We'll use this as the original length, not this, right? Some people use this as a mass. So some people use this as the original and then use the difference as the extension, right? But for our purpose, we will use right? We will use this as the original length, right? What will happen? What will happen as I add mass here? What will happen? It should extend, right? So if I were, I know it's kind of hard to see what the original length is, right? But let us see. Right, if I started here, the original length is right here. Right, I'm sure if you've seen that online, right? Okay, I'm going to add on a mass. Let's see what will happen. Right, if I add on a mass, that's the original length. And they would recognize that from here to here, there is an extension. You'll see that? If I add on a next mass, right? If I add on a next mass here, right? You will see that the extension, so you can see it there, right? You will see that the extension went a little bit lower. That's okay. But here's one of the important things that Hooke's law talks about, right? If I were to take off these masses, it should go back to the original length. Let's see if that happens. Yeah. So let's be from the original length. If we can take a look up there, right? You'll see it went back to the original length, right? So whenever that happens, whenever I add a mass or a force, and I get an extension, and I could remove that mass, and it goes back to the original length, then it obeys Hooke's law, right? I don't want to do it to this one, but what will happen if I keep adding on masses? Right? There will be a point in time when the extension will be so large. If I remove all the masses, this becomes what? Permanently stretched, right? When that happens, the spring or the elastic medium will no longer be Hooke's law. Okay? So if we look at what happened here, what we could say happened to the force and the extension. As I increase the force, what happened to the extension? It increased, right? And when I kind of remove the force, the extension dropped. So these two are what? Directly related, right? So I could write it like F. I could write it like this. F is proportional to E, right? And I could turn it into a nice formula, right? Good job, T-Bash. F is equal to K. You're okay with that? Some books might have F equals to Kx, right? It's based on what symbol they use for E. I am using E and F. You're okay with that? Right? And this K, because we did our experiment with a spring, it's called the spring constant. That's okay? And you may have done this lab, and in the lab you had to find spring constant, right? So let's see how we can find spring constant if we had carried out that lab, right? You would have recognized that we got a set of mass values, and then we read off some extension, right? So let's pretend we use 20, 40, 60, 80. Let's pretend it was in kilograms. How do I convert this kilogram to a force? And I'm making up some values here for extension, right? Yeah. How do I convert this mass value? Because remember, these are masses, right? For the exerting a force, right? How do I convert the mass to a force? Multiplied by 10. Okay, I'll take that, but multiply by gravity, right? Because the force that these masses exert is called your weight. That's okay, right? And the practice that we are going to do, pay attention to the SI units. All right. So how do I convert mass to force? Multiply by gravity. We will assume gravity is 10, right? Right, so this will give us 200, this will give us 400, this will give us 600, this will give us 800, right? So what's the objective again? The objective is to find that K value, right? Anybody remember what we could do? All right, let's say the question said, plot a graph of force versus extension. Because it's directly related, it might look something like this. Correct? Anybody could guess? I didn't give you that graph, sorry. I should have given you that graph, right? Directly look like this. Anybody could guess what inversely looks like? Down the slope, right? Directly up the slope, inversely down the slope. All right? If you get a graph like this, Aidan, that graph is saying that the things are inversely related. If you get a graph that looks like that, it means that they are directly related. Okay, nice. So I have the big question now. I have the graph, right? We get all the values and we plot a graph of force versus extension. How am I going to get spring constant? Subject formula. Well, in the end, you're kind of doing that, but what you have to do to get that back. Talk about it when you're plotting graphs. Right. Let's use what Ethan said. Ethan said to make K subject here, right? What will that be, Ethan? Right. So how am I going to get F over E from there? How am I going to get F over E from a graph like this? Think you did it. Why Cahoots? I think I asked them why Cahoots. Right? Narissa, that's for the answer there. Right? Narissa said if we find the gradient of this graph will give you spring constant. Anybody remember how to find gradient? Y2 minus over x2 minus x1, right? Which is whatever on the y divided by whatever on the x. Right, Javi? So if I find the gradient, I am technically finding f on e. And what is f on e? P. That's okay? If the quantities were switched around, right? If the quantities were switched around, then you gotta take your time and make this up again. Same principle of work, right? But you just had to make to be a little bit different, slightly different, just upside down. Right, Isaac? Right. But Isaac, about problem, Isaac. Remember, I was saying, right? That if I keep loading this, right? If I keep loading it, what will happen to this after a while? It wouldn't go back to the original, right? So if I wanted to sketch that entire graph, if I wanted to sketch out that whole graph, how do you think it will look? Right? So how you think that graph will look, right? So we keep adding on the force and the measure and the extension. Everything nice and dandy when it's going back to the original line. What will happen after? First, it will go flat, you close, but not flat. Now, what would happen? It wouldn't behave like this anymore, right? It will no longer be F is proportional to E, right? What will happen is that it will start to behave like that, a little curved. Right? Something like this, I have a curve. And of course, there's a point when there will be no more extension. That point is when the spring breaks. Right? So this straight line part here, that is the part where it obeys Hooke's law. Okay? Sometimes you might see they just draw back a line like this. Right? So up until the straight line part, that's where it obeys Hooke's law. And that is called the proportional limit. Okay? And then you have a little bit after the proportional limit where it stays elastic, right? So up until here, we call that the elastic limit. And after it past the elastic limit, we call this the plastic phase, right? Or we call it plastic deformation. Okay, so these are the things that we need to know about Hooke's law, right? So does Hooke's law apply up here? No. Hooke's law only applies right here. That's straight line part, right? Okay. Right. And I didn't want to copy it out because to you, but it's already in the notes as sent you, all right? But it's nice we did just make a little note of these little things here because I'm going to do a question on that. Right, so that's the principle of Hooke's law here. Just make sure you follow everything that we have in the little note there. And then we're going to jump that question, right? Right, so Hooke's law basically states that the applied force for an elastic material is directly proportional to its extension, provided that the elastic limit is not exceeded, right? Remember, these notes are sent them in the WhatsApp group and it's also on the LMS, right? Okay. Well, yeah, I'll explain the proportionality here. Here we have the graph a little bit, but you will notice that this graph is the other way around. It's extension versus load, right? And the shaded part there is where it will be Hooke's law. Right, I'll just explain it now. I was just explaining on that underneath part, proportional, right? Directly and inversely. Right, in 1960, Roberta Hooke investigated the relationship between an applied force on a material and its extension. Right, its law states that the applied force for an elastic material comma, to be comma there, right? Its extension per an applied force is directly proportional to the elastic proportional, provided that the elastic limit is not exceeded, right? We have F proportional to E, right? And we have a little formula there. And I also gave you the SI unit, right? Please notice that your force has to be in newtons, right? And the last part is what? Right, right? The force is in newtons and the extension is in meters. Okay? Right? It's not totally wrong if you have the extension in centimeters. What you have to remember is that the spring constant will be in Newton per centimeter. Ready now? Remember that, right? Right here we have a small calculation. Take a look, see if it makes sense. Right, so you have a force here. Again, when you read the question, underline all the important parts there. Right, we have a force. The force is 5 newtons, and it gives you an extension of 10 centimeters. They want us now to find the force needed to give an extension of 0.25 meters. Very important. We assume that Hooke's law is not exceeded. Right? If Hooke's law is exceeded, we cannot use that. That's okay? Okay, what is it? First thing they did is they solved K. Right? K is equal to F over E. F is 5 and E is 10. Right? F is 5, but instead of using 10 in centimeters, what they did? They work in meters. So they end up with K being 50. Right? K is 50 Newton per meter. Right? And once you know the value for K, right? Once you know the value for K, we can plug it back into the formula now. Right? We can plug it back into the formula. F is equal to KE, and we'll get F is equal to 50E. All I have to do is plug in the E value. That's okay. All right. So try this one. Number one. Try this one. Okay. Same concept. Same concept. When a force of 10 newtons, when a force, no, I give you one, right? I changed this slightly. When a force of 10 newtons, so I'm changing it slightly, right, online? And again, some people look at the message answer, right? Right? When a force of 10 newtons is applied to a spring, when a force of 10 newtons is applied to a spring, its extension is 20 millimeters. Its extension is 20 millimeters. Full stop. Find the extension. Find the extension when the force applied. Find the extension when the force applied is 35 newtons. Again, assume that Hooke's law is not Hooke's law is a field. Now make it up. Find the extension if the force applied is 35 newtons. The time, what's the first thing you're gonna find it out? First thing I'm gonna read it. After you read it. Come on the board. But I will be out fast. Okay, right. So the first thing you have to do is to find K, right? I take your time. Right, I'm gonna give you a find key and then find. Ready enough? We will see about. Are done? Yeah, we finished it. I'm checking. Have you just go checking anybody? Come on, Rita. Right, tell me what's the first force to give you done? The force is 10 and the extension is what? 20 watts. So therefore you have to work in what? You have to work in meters, right? So how much is that in meters? Right, well, you can just take off milli and just write 10 to the minus. Right? Right, next step, what's the formula to find K? K is what? K is what? Online message answers. K is what? F over E. Right? So F is 10 over 20 by 10 to the minus 3. What is that? 5,000. Right? SI unit, please write the SI unit, right? Everybody get up? 5,000. I know I just listened to all you. Yeah, it should be 5,000. Take it back and see. Put in the calculator. Jump for the whole exponent, right? Oh, it's again. Calculator. 20 divided by 1,000. So the force is 10, but it's the same thing, right? That's all. 500. Okay, check it back. 500. I thought it was 5. All right, yes, 0.5 divided by 10. Okay, yeah, it's 500. It's 0.5. Nice. Last part. What do you want, Fishish? What's the last part? What do I find? So we don't want to find what extension of course. So E is equal to what? Use a little math skills there. E is equal to. Now rearrange the formula for me. What's the formula for E? So F over K. Right now the K here carry across. And the F is what? 35 and K is 500. F is 35, right? And the K is 500. How much is that? 0.07. What's the SI unit? Meter. Right? Are you okay with that? Yeah, let's go again. Next one. Right? Nice happy to achieve no meters, right? Not Newton meter. All right, so copy down. Let's go again. If you draw that graph, boy, I really hope we can draw that graph. So, all right, let's go. Next one. All right, that is that's that hit this here earlier. Hold on, yeah. Try the first part, then I'll just slide it down, right? You don't have to join. Just write down. Hold on, yeah. Jan 2019, number 3, part C. Jan 2019, number 3, part C. Right now, you're picking kilo on the help us out here. Part 1, 2, and 3. Take your time. Very simple, like what, 5 letters, 6 letters. Somewhat. Very easy stuff there, you know. Right, you pick on here. Let's pick on somebody new now. Let's pick on somebody. Can I mess with the name again? Samir. Right, Samir. What do you think about part 1? I don't want to rush him. We need more time down. All right. Take your time. Take your time. I'll go in the game next week. I can't take no more. I'll miss something. Right. I press on the next week. That would jump. When it does. Huh? Oh, that would. Take it right. Right now, for I will. So, Right, yeah, where Samir O to A Samir. Hooks B to A. Nice straight line, right? So what's the formula? What's the relationship between F and E? K equal, all right, yeah, I'll take that. I'll take K is equal to F over E. Ideally, I would like to hear F is equal to K. Same thing, right? Good job, Samir. Right? Elon. Don't forget it, Elon. Part two. Part two is here. You're saying that? State the point at which the elastic limit is located. So just write in one letter. Which point there is the elastic limit? Right here. So Elon, where does the elastic limit located? At A. Anything beyond A it starts with Q. You're seeing it? Anything beyond A it starts with Q, right? Next part, three there. State a reason for the shape of the segment AB. Right next to Sheila. What's the name again? Austin. Sterling. As well as Sterling. Why did AB happen? Yeah.
Stretch across its point of extension.
Okay. Nice. Right? That can work. But I would like to also hear the elastic limit was exceeded. Right? A to B, the elastic limit was exceeded. Right? And what is called that region? What happened in there? Plastic deformation, right? Now make it look real smart, right? So A to B, the elastic limit is exceeded, right? And it's also called the plastic deformation, right? Nice. Right. Could be speeding that graph, boy. All right. 2008 might be a little too long for now. But then the next one in 2030. Right? We have to plot the graph, we have to find the gradient, and online, I took the graph paper home, right? I'll give it in. Quick. See if we can plot the graph for one audiences. Or if you have one in Europe, go for the graph. Yeah. No. What we ask about for that? Tell you. And if I tell you, no, it's the graph. Right. Yes, it's still not going, but right. I know it might be a little challenging, but I want you to plot the graph and then find spring constant. right? Here, pass again, do that now. So I done Coleman, I'll check it, right? One line, once you finish, take a picture and send it to me, please. Alright, take your time, plot the graph, find the gradient, and then I want you to find spring constant. Right, we don't have much time, so I want you to try and see how fast you can do it, right, Arissa? Make sure I see your graph, Salim, Mr. Gerard, especially you, I want to see your work. Everybody else is Narissa, will be good, Nathaniel, when here, Serena. The one of these Serena's here, they were trouble. Mohammed is a good one. We're weekend. Arissa, what's your graph, right? Take a picture and send a graph. You are Mr. Gerard. Take your time. Plot. Which one going on which axis? Line going on the and one going on the X. The load, right? Hurry up, Serena. Look at graph page quick. Or draw up some lines. Hurry up. Yeah, quick. Right, remember to use the right scale. What's back is scale. What's back is scale below. Right, what's a good scale for the x-axis? What's a good scale for the x-axis? 2 centimeters is 2. Oh, 1 is 2. 1 is 2. Okay. Oh yes. Right. So every 1 centimeter. Yeah. Sorry, every 1 centimeter. 1. 1, 2, 3. Out. Right. Every 1 centimeter is 1, or every 2 is 2. Right. Plus up your graph. Nice. Jordan sent a graph already. A picture. Oh, now see what happened there. So at point 2 is 0.36 and at point 4 is 0.35. What y'all think happened there? What happened there? We had a little mistake, right? Because as the force increase, the length should also increase. So most of that's a typo there. Right? Here you can do for us. Fix it quick and put 2.6 as the first one. Change the first one, right? And remember, like Jared, remember you want to get a gradient, so it's one line you have to draw. What you call that line again? What you call that one line? On the side, yes, it's a straight line. What? Best fit line. Right? You have to draw the best fit line. Hurry up. Right? So you need to draw one line, right? Oh yeah. What a good scale for the x-axis, for the y-axis. Yeah. What a good scale for the y-axis. 1 centimeter is how much? I'm not sure they have formula method, but you can start with something easy. 1 centimeter is how much? 0.1. What? 1 centimeter is 0.1. You can double up. Could you go more than that? Could you go 4 centimeters is 0.1? Can I work? Can I work? Check and see now, please. 4 centimeters is 0.1. Remember, your graph has to be more than half, right? Right? 4 centimeters is 0.1, right? So you might be able to get it to go all the way down. And some of the graphs are real small, right? Less than half of the page. Go ahead, do it, still on time gradient. Maybe there. Feel there, right? Yeah. Right. Right. Right, I see how you Thanks. Right. The force is there. That's the force part is there. Right? And this is the next part. Right? What's that? Right, that's all under a specified line, right? I repeat the front. Right, somebody else check it out, so. Somebody finishing out on my phone. That's, you cannot pitch it, many. That's why it's the next access, so once that's okay. It's on the x-axis. Right, Serena, that's looking okay. Right, Serena, you're looking okay. Right, I sent one in the group. Right, I sent one in the group so you can look it up. Wow. I want to see our next graph, analyze your graph. Right? The best fit lines that are common. So I want to show you, I like gradient, I talk to the next part, but find the gradient of your graph, right? Find the gradient of your graph and you can always fix it after. Alright, so let's take a look at what the graph's supposed to look like, right? Right, so you remember, Nathan, where your graph, see your graph? Yeah, before you leave here, join that. Right, what you tell you. So your graph's supposed to look like this. If you plot them properly and they best fit line properly. How you know when you best fit line and when you connect points or draw a curve. How you know when you have to draw a best fit line and then a curve. If you see fine gradients, best fit line. Right? If the question says draw a smooth curve, well, connect it into a smooth curve, right? But I don't want you doing this, right? Right? I don't want you doing this, right? Just connecting points like that. Right. So when you found the gradient from this graph, what you got? All right, so let's find the gradient quickly. Let's use this here, right? So I am looking for an easy point to read off or reading off here. That point there is 0.6, 0.6, 0.2. And I'll pick something easy going up the road here. I'll tell easy one here. Right? That's looking like 15. That looks like 15 on the x-axis and 0.75 on the y-axis. So I'm going to work it out. 0.75 minus 0.2 is 15 minus 0.6. How much is that? Right? I try to read off points that are simple to read off, right? How much is that? Can you help with that? Zero point 0.038. Right? It might vary slightly on your graph, right? But your best fit line should not go through the origin, right? It should cut the y-axis. Okay? All right. So let's look up here. How we getting spin constant here, audience? How we getting spin constant here? What does the gradient there represent? What does the gradient here represent for you? Well, what's on the y-axis? Huh? So, what does the y-axis represent? What quantity? Length, yeah, length. And what does the x-axis represent? Force, right? So, right, let's take the extension a little bit, right? So there's no officially extension. Right, question. Oh, again, spring constant. Okay. Gradient is E on F. How am I getting K? Back at the beginning of the class, I gave you a little hint. With the pick on scenario. The gradient is E over F. How again? K. K is what? How you find K? F over E. But I have E over F. So what to do? Put it around. Flip it over, right? That'll be 1 over 0.03. Okay? Just flip it over. 1 over 0.03. How much is that? Six point three. 6.3 Newton per meter. Okay?
26.
Huh? 26. 26.3. Okay? And before we go, last thing. Right? This question will go to Cheetah. You can see the graph. Okay, now you can't see the graph. Ethan, you can see the graph from there. Here the last part of the question is. The last part of the question says, what is the original length of the spring? What do you think is the original length of the spring? Please remember, these are the forces, these are your lengths on that side. What do you think is the original length of the spring? Online? Anybody know it? What do you think, Ethan? Yeah. 0.26, so you get up. So this point now. Right? Would the original length have a force attached to it? To think about what we had here with our spring. That's I lost. Right. Would the original length have a mass on it? No. So look at your graph and look at this graph here. Let's all have one answer. Look at this graph here. How are we going to get the original length? Anybody? Very sense. Finally, very sense. Okay. Done. Yeah, what a guess there. Alex, have a guess? Yeah, Ethan. What's your guess? 0.2, that's very close. Watch this here. If you read off your y-intercept, right? If you read off your y-intercept and the force here on 0, yeah? Nathan? So what would the value be, Nathan? Can you get it right? Yeah, I'll make it right. You clean there. Right? The value is the y-intercept. Okay? The y-intercept is when the force is 0. So from analysis diagram, that's 0.18. Just why? Banana? Because that's the point when the force on it was 0. Right? It might vary slightly. But for those who draw the line back to the origin, like that, you would have gotten it wrong. Because your graph would have said 0. Alright? So that it should ideally have gone back to the y-axis. Online, Richie? Are you okay with that? Celine, Jared, Narayan, you're okay with why the value is 0.18 for the original line? Yeah, no? Understand? Alright.